Okay, guys, so here we will talk about the some practice about chapter 8 about the valence bond theory and the molecular orbital theory. And now, before starting with the practice, with some example, I will just go quickly and review about some important things, some important key that you need to understand it, memorize it before working with this question or example. First of all, Lewis structure. It is the key for this chapter and also the previous chapter, okay? For the shape of the molecule, hybridization, polarity. So Lewis structure is very important. So I will go with the Lewis structure right now, and you will see like this rule. Okay, guys, so I will just turn off the camera so you can just focus on the practice. Okay, so here we have this flow chart. Okay, so what do we have here? We have this molecule, for example, SO2. Draw the skeleton structure. I know we already covered this chapter 7, but I will go through it quickly. Skeleton structure, we have the S. We try to make a symmetric molecule, so SO. Okay. Now, total valence electron. Sulfur, it is 6 plus 2 times 6 for oxygen. Total will be 18. So we will have 18 valence electron. Now, total available electron. Look at here. We make this connection for the skeleton structure. We use 2 bonds. So each bond 2 electron. So 18 minus 4, because we have 2 bonds. So it will give you 14. So this is the available electron, AE. Now, how many electron we need? Okay, the needed electron. We need to make each of them achieve the octet. So we need 2 here. So 6 for each oxygen. And here 4 for the sulfur. So we need 16. Now, you will answer this question. If AE equal NE, this is the Lewis structure. This is the structure. Okay. If AE less than NE, so here we will insert double bond. Insert double bond, or sometimes triple bond, or sometimes 2 double bond. It depends, like how many electron deficient or short. So here we are 2 electron short, so we need just 1 double bond. So I will insert 1 double bond here, make each of them achieve the octet rule, and that's what we have. Now, be careful, guys. We have 3 situations. First of all, AE, the available electron, equal the needed electron, or AE less than NE. It's the second situation. The third situation, which is also important here, I will go through it. It is when we have the available electron more than NE. What you have to do in this situation, you have to expand the octet rule. So look to this example, guys. So we will do the same things what we learned in the previous chart. Draw the skeleton. Total valence electron here, 28. The available, after you make the connection, we have the 3 bond here. So minus 6 electron. So what's left? It is 28. Now how many electron needed to achieve the octet rule? Each fluorine we need 6, and Cl just 2, so 20 electron. Now, the third situation is available electron larger than the needed electron, so expand the octet rule. So here, expand the octet. That means the central atom could have 2 more electrons. That means 10 around it, or maybe 4 more electrons, 12. Okay. So here, complete the octet rule. We have 2 electron extra. This 2 electron extra, we will put it in the central atom. So we will have 10 electron around the central atom. Be careful, guys. Try to practice with the Lewis structure. But for this chapter, for the previous chapter, it is very important, as I said. Okay, now let's look what else we have. How to figure out the molecular geometry, the shape. Okay, so look here, guys. We have don't forget the AXE, sorry, notation. The AXE notation, it tells you how many atom, terminal atom, and how many lone pair. This is, let's say, M, this is N. So this is N, tell me how many lone pair. M, how many bonded atom, or how many terminal atom. And this A, it is the central atom. So for example, look here, I have H2O. Of course, we need to draw the Lewis structure. So look here, will be AX, how many terminal atom, 2 hydrogen, so it will be 2. E, how many lone pair for the oxygen, 2, so it will be AX2, E2, like this one. What is the shape? It will be bent. Okay, so this table, it will help you to predict the shape of the molecule if you have 2 group, 3 or 4 group. The other table, it will show you when you have 5 or 6 group. So look here, we go to that table. Now we have AX5, just 5 atoms, so it will be trigonal. It will be trigonal. Let me just make this bigger. So it will be trigonal pyramidal. Trigonal pyramidal. We have 1 lone pair, so it will be seesaw. We have 2 lone pair will be T-shaped. 3 lone pair will be linear. Now let's go to the 6th group. When we have just AX6, just 6 atom octahedral, 1 lone pair, it will be square pyramidal. 2 will be square planar. If it's a 3, will be T-shaped. Then if it's 4, will be linear. Okay, now a quick way to predict the polarity also. It's working most of the time, but not always. Be careful with it, guys. I just try to give you something that will help you quickly predict the polarity of the molecule. So first of all, you need to write down the Lewis structure. Classify the molecule as AXE. How many X we have? How many E? How many terminal atom, or how many lone pair? And decide on the geometry, what it will be the geometry. Consider AX bond and answer the following question. Are the terminal atom identical? Are they the same? If it's yes, possibly non-polar, depend on symmetry. If yes, so possibly non-polar, but depend on symmetry. We will answer question B. So we have A and we have B later. If you say no, say from the beginning, polar. As I said, it's working most of the time, but not always. Be careful, guys. Now, we said if it's yes, possibly non-polar. Now let's go to the B. If we have identical atom, are the AX bond arranged symmetrically the same around the central atom? If it's no, not the same, so will be polar, okay? If yes, will be non-polar if the answer to A is also yes. Now, presence of lone pair often considered polar molecule, but not always. Be careful. So when you will see like a lone pair on the central atom, say from the beginning, is a polar, but not always. Be careful, guys. Depends on the symmetry. It affects on the symmetry of the specific molecule. So for example, NH3 is a tetrahedral shape and would be non-polar if it were trigonal polar with a hydrogen in all sides. But the lone pair doesn't allow the symmetry, turning it into non-symmetrical tetrahedral arrangement. But as I said, guys, not always. Look at here. I will give you one example like XeF4, for example, XeF4 has two lone pair in the central atom, two lone pair, but it is not polar because there is a symmetrical distribution of the lone pair and the F1. While H2O, oxygen has two lone pair, it is a polar. So be careful, guys. As I said, it's working most of the time, but not always. Okay, now the hybridization. Some more things here we have for starting with the practicing. Okay, start by writing the lowest structure. Here, guys, always lowest structure. Starting with the lowest structure is very important. This is the key to solve all these questions. Okay, start writing the lowest structure for each species. Determine the species AXE notation, then the extra electron pair in a multiple bond will not located in the hybrid orbital. That's the number of terminal atom, M equals the number of bonds in a hybrid orbital. So we don't care. We are not counting the double, the harmony bond, harmony terminal atom. So here, just take this example, AXMEN. This is the M, the terminal atom. This is the N. It is the N share, the pair of electrons, the lone pair. So you will count the M plus N. What will equal? If you have, look here, guys, if you have just two, starting from two, because two group around and around, so it will be sp. 3 sp2, 4 sp3, 5 sp3d, 6 sp3d2. That's what is the hybridization. As I said, hopefully this will help you guys help to figure out the hybridization, the shape of the molecule, everything. So look at here, guys, to this table that will give you some idea about the hybridization.